we're going to talk about that today. Yeah. Any other questions? Okay. I'm going to finish up with one piece of unfinished business from last time. So we've been talking about the set NP, which contains every algorithm we've studied this semester. We got the problems in the set P, which are problems that can be solved, or search problems that can be solved in polynomial time. And then the presumably, but not, the presumably larger set NP, which are problems that can be verified in polynomial time. But there are problems harder than that. And in fact, there are problems that are so hard that they can't be solved on a computer. Proofs like this, proofs that there were problems that could not be solved on a computer, were first created in the 30s, before there were computers. So people like Alan Turing were studying the limits of computation before there were really tools to do computation with. So I want to show you a couple such problems. And when I say there are problems that can't be solved on the computer, I don't mean metaphysical, philosophical questions that are hard to answer. I mean problems that are easy to describe, but nonetheless can't be solved in all cases. So the first is finding roots of Diophantine equations. So this is an example of such an equation. It's just you've got polynomials in multiple variables. So x cubed, y, z, 3 variables, a polynomial. That's a monomial. You add and subtract such terms. Equations like that, where the variables are constrained to lie in the integers. The problems are constrained to be integers. The variables are constrained to be integers. No matter how hard you write, no matter what computer you use, what language you use, it's impossible to write a program to solve any such equation. In general, you can't write a program that'll work all the time. Yeah?
Does that mean do we not have any way to solve that mathematically, or is it just computers can do it?
If there's a way to solve it mathematically, the computer could solve it. Right? They just follow the same steps a person would. Okay? Yeah?
Like my first thought with that is that you could just use trial and error or brute force.
Okay, so let's think about that. First of all, let's make sure this is a search problem, so we're asked to find some integers x, y, and z in this case. I'm not saying you can't solve that equation, but you would find integers x, y, and z that would make that equation true, or you would report that there are no such integers, no solution. So why not just do trial and error? Why not just start systematically trying all values of x, y, and z? Yeah?
There's just no guarantee you're going to find a solution.
There's no guarantee what?
You'll find a solution.
Okay. So he said there's no guarantee you'll find a solution. So if we wrote a loop, a triply nested loop that tried all values of x, y, and z, if there's a solution, we would eventually find it. But what if there's no solution? The equation is not guaranteed to have a solution. So what if there's no solution? What would our program do? Yeah.
You have no way to know when to terminate because there's always going to be more possibilities.
Right. If there's no solution, you've got to stop at some point and say there's no solution. And this would just, if there was no solution, the strategy I just described would just run forever. So we wouldn't be able to say there's no solution. Now I'm not going to prove to you that this is not computable, but I'm just going to give you an example of a simple problem. It's simple to describe. Now, but it has no solution. Why isn't this problem a member of NP? It seems like here's my thinking. If this is a member of NP, then it's just as hard and no harder than lots of other problems that we know how to solve. Right? We can solve the travel. We can find Hamiltonian cycles. It just takes exponential time currently. So any NP-complete problem we have, we can deal with in polynomial time, in exponential time. So isn't there a simple argument this is a member of NP? If someone gives you a solution, gives you values of x, y, and z, and says, here, this is a solution to the equation, can't you just plug it in and see if it's an answer? Yeah?
like you said, you'd never be able to tell if it isn't an answer.
Well, no, if someone gives you, says X is 57, Y is 102, and Z is 15, says that's a solution to that equation, I could plug those in and see if the left-hand side is the right-hand side. I don't have to search for an answer, I just gotta plug them in and see if it works. That would seem to argue that problem is a member of NP. Yeah.
Well, for a problem to be solvable, that isn't just the act of having a solution, it's being able to routinely and predictably find the solution.
Well, that's true, but right now I'm backing up from worrying about whether it has how to solve it. I'm just arguing. I'm trying to argue that it's a member of NP. To be a member of NP, it just has to be polynomial time verifiable. Yeah.
Doesn't it also have to reduce to another NP problem?
Well, you're thinking of NP completeness.
Oh, okay.
Okay. I'm just trying to argue it's a member of NP. Yeah.
Well, that ignores the case where it doesn't have a solution. So if someone tells you, oh, this problem doesn't have a solution, there's no way to verify that in polynomial.
But that's not, there's no requirement, for membership in NP, there's no requirement that if someone says there's no solution, that you have to be able to verify that. For example, take the Hamiltonian cycle problem. Given a graph, there may or may not be a Hamiltonian cycle. But the only requirement for proving that problem is a member of NP is to say, if someone gives you a potential cycle, that you be able to verify. There's no requirement that you be able to verify that there is no solution. Yeah?
Because if the numbers are too large, it takes extra rounds of time to verify.
Exactly. The problem is it has to be verifiable in polynomial time. So this is pretty small. It doesn't take many bits to write that down. But a solution could potentially be extremely large. Imagine a solution with billions or trillions or 2 to the 100th bits or whatever. So you have to be able to be a member of NP, you have to be able to verify the solution in time proportional to a polynomial in the length of the input. And in this case, the output, the solution could be vastly larger than the input, and so it could take a very long time to verify. So it's verifiable, it's just not verifiable in polynomial time. Now, it's a long way from saying this is not a member of NP to proving that this problem can't be solved. And this isn't the time or place to do it. I'm going to show you a different problem, though. Okay? This is a very famous problem called the halting problem. And it's given a program and its inputs, determine whether or not it terminates. So, for example, that's something a compiler would like to be able to solve. Compilers would like to be able to find infinite loops in programs. It'd be interesting if a program that solved the halting problem existed, you'd be able to take a program, like some Java program, and provide the program and its inputs to the method, and it would tell you back whether or not the program would halt when it ran. Yes or no, the program halts when it runs. Okay? You can't do that. The halting problem isn't computable either. But what if we could solve the halting problem? Suppose we had a method H that solved the halting problem. Would we be able to solve that problem?
Yeah.
Okay, how would we do it? We have H if H existed. Yeah.
Could you give it the program that tries to solve the equation, and then it would tell you whether or not it halts eventually, and that would be
Yeah. So what you do is you take the program that you got a program that takes this as an input and tries all the possible values of x and y and z and tries to find a solution. And that works. That will eventually find a solution if one exists. The problem we had was it may run forever and we'll never be able to report, oh, a solution doesn't exist. Your first step could be take the program, feed it to H, and it'll tell you whether or not that the search method for that's going to halt. If it says this will never halt, you can say there's no solution right away. If it predicts that it will halt, then you just run the program. Eventually it will find the solution and report it. So, anyway, two examples of problems that are so difficult that there's no algorithm to solve them in all cases. Now, it turns out that if you assume that the halting problem can be solved, if you assume that if you have it's called an oracle. If someone gives you an oracle that can solve the halting problem, then there are lots of other problems you can solve there. But there'll still be problems even harder than that. The cold hard truth is that there are, there are different degrees of infinity. There are an infinite number of possible computer programs, but there's way more possible problems than there are computer programs you can possibly write. So anyway, this is just a glimpse into an area of theoretical computer science we haven't talked about. That's if you take 3100, if you've taken 3100, that's the sort of thing you talk about at least for part of that class. There are limits to computing. Okay. So we spent this time talking about problems from NP and NP-complete problems, and kind of, there's this, people pretty much believe that NP-complete problems cannot be solved in polynomial time. Nevertheless, a lot of the problems that are NP-complete are problems that we need to be able to solve. We need programs to cope with them. And so you don't just say, this problem requires exponential time in the worst case and give up. You just try your best. You're not going to come up with an algorithm that always works, but you can maybe find one that works most of the time, or find one that works really well for the cases that occur in practice. So what we're going to look at now and next time are approaches to dealing with NP-complete problems. How do you deal with these problems that don't have efficient worst-case solutions? Because it happens a lot. So most likely, as I've observed, such problems occur exponential time in the worst case. So you can concentrate on the other cases. So here's some approaches. Sometimes there are special cases. So maybe you can't solve the problem in the general case, but if you make certain assumptions to simplify the problem, then you can solve it. So that's one thing you can study, are special cases to the general case. And so algorithms like that solve special cases, you can come up with algorithms that are correct all the time in these special cases. Correct all the time, but they're efficient most of the time, i.e. they're efficient for the special cases. Okay? So instead of concentrating on efficient solutions for special cases that blow up when you have the general case, you can try to come up with efficient algorithms that get you an approximate answer. So those algorithms would be approximately correct and be efficient all the time. Now, what good is it to have an algorithm that's approximately correct? What does that mean? I mean, what would it mean to have a sorting algorithm that was approximately correct? Would that be of any interest? Yeah?
I mean, if we get something that we're 99% sure about, that's pretty darn close to the right answer, so it seems like something we could use.
Okay. What's your take?
So, like, what we looked at with RSA, this idea that, you can be sure with, 99.9999 whatever, that something is a prime number, that's good enough, right?
Okay. There's two ways of looking at it. So when we talk about approximation algorithms, we're generally talking about optimization algorithms, optimization problems. So there, when I say something's approximately correct, it means take that as approximately optimal, almost optimal. So maybe perhaps you can't efficiently find the exact solution to the traveling salesman problem. But if you could find an algorithm that would get you really close to the absolute best answer in a fast amount of time, that might be good enough. If UPS wants to drive its trucks efficiently in a cycle and get back to where it started, and it takes too much computing power to figure out the absolute least amount of gas they can use to do that, but you can efficiently determine the least amount of gas to within 5%, say, then that might be good enough for UPS. It just needs to get close to the optimal. It doesn't absolutely have to have the absolute best solution. Now, there isn't any approximation algorithm that comes within 5%, but there are, depending on the problem, approximation algorithms can make various guarantees and come close. So think about approximation algorithms as being good for optimization problems. Sometimes you're reduced to just trying all the possibilities. So when you're doing search problems, trying all the possibilities means using a backtracking approach. Now, we have problems that try all the possibilities. When we did dynamic programming, we were constantly writing programs that tried all the possibilities. Why don't we just use dynamic programming here? Yeah?
You would take an exponential amount of data.
Okay, so where dynamic programming works is when you're making an exponential number of recursive method calls because you're trying all the possibilities. But it turns out that there are only a polynomial number of different problems. So dynamic programming works when it turns out that your solution is solving the same problems over and over again, so you cache the solution, look it up later. But you can have problems where the number of distinct subproblems is exponential, and so now your cache is exponentially large. So dynamic programming doesn't always bail you out. So with backtracking, you enumerate all the possibilities to find a solution. Intelligent backtracking tries to be clever about the order in which you consider the possibilities. We'll look at an example of that next. And then for optimization problems, again, you're doing using a backtracking approach. But you can make backtracking approaches more efficient in that case, exhaustive search more efficient in that case by using a technique called branch and bound. And rather than try to explain it, I'll just show you. Yeah?
Are approximation algorithms generally or sometimes built in a way that if you run the algorithm twice, it'll be better than just once, so you can get an approximation that's close enough?
Well, that would be, I guess, if you had a randomized approximation algorithm that would work that way. So there are algorithms like Monte Carlo method where you're probing at random at a problem to try to find a solution, and you might get slightly different ones that way. So we'll come back next time and look at approximation algorithms and special cases to famous problems, or maybe the end of today, depending how fast we go. What I want to look at now is these techniques of backtracking, intelligent backtracking, and branch and bound as sort of general purpose ways to solve search and optimization problems when there's no better way. And to do that, I'm going to look at some actual code, and then we'll look at some slides to tie it together. Okay, this first problem is 3-SAT. So let me remind you about 3-SAT. In fact, I'm going to run the program here. Okay, so this is using a backtracking approach to solve a 3-SAT instance. So remember what 3-SAT is. It's a bunch of clauses ANDed together, where each clause consists of a variable or its complement in the truth value sense, or together. So this part is saying not x23 or x41 or not x38. And our job is to find an assignment of truth values to all these variables that makes this massive thing truth. And this is keeping track of how many recursive calls it have made so far, trying to find a solution. So it's about 600,000 recursive calls. Now, I'm not sure how long this would take. I don't propose to stand here while it works. Okay? Now, 3-SAT may look completely esoteric to you, but as I've mentioned, it has practical applications in program verification and hardware verification. And there are applications where you might have hundreds of thousands of variables. This one I think has maybe, I don't know, I can look in a second, maybe 50 variables. And many more clauses. that occur in practice. And I was at a talk once by someone that knew a lot about this sort of thing, and what he said was that the best algorithms that are used in practice can solve those massive problems that occur when you're doing verification really quickly. So deal with 100,000 variables and several million clauses quickly. But those same algorithms, if given randomly generated three-set instances like this one is randomly generated, might only be able to deal with hundreds of variables. So there's something different about the problems that tend to occur in practice versus the problems that occur when you generate things randomly. So let's think about how you would solve this problem. You're presented with something like this. You can represent it in whatever data structure you want to internally. How would you go about finding an assignment of trues and falses to these 50 variables that makes this whole thing true, or report that there is no assignment that makes this whole thing true? What if you had to write that program? What if this was the caddis problem? Yeah?
Just start with the first clause and find what makes that one true, go to the next one.
Okay, so he's suggesting you go to one clause and figure out how to make it true. The problem is there's multiple ways to make it true.
But for essentially do it recursively, so in this first clause you have assignments,
Mm-hmm.
and then you check them against the next clause up until you get one that doesn't
Okay.
work, and then you go back to the beginning.
Okay, so that's one way. I'm going to propose a different way, which is instead of concentrating on the clauses, concentrate on the variables. So we got 50 variables, let's say. Just make a list. Pick the first variable and say, maybe this variable should be true. So if you assume that the first variable is true, how does that simplify the problem? How could you simplify the problem if you knew the first variable had to be true? Yeah?
Take all the clauses where it being true just automatically makes everything true and disregard them.
Okay. So if x18, let's say x18 was our first variable, and we decided x18 was true. We just remove this whole clause from the problem because we already made it true. The idea is to make every clause true. So we just take this one out. Okay? What about, are there other clauses we could simplify if we decide x18 is true? Maybe not one up there, but can you describe one we could make? Well, there's one. Right there it says x18 or not x25. We could get rid of that one. Any other, what other ways could we simplify if we make the assumption x18 is true? Yeah?
You know, anything that's not x18 could be, needs to be something else true.
Okay, so let's look at this one right here, not x00 or. What if we decided that x00 was true? What would it say about this clause?
The pluses are orders, right?
Yeah, pluses
so
are orders.
not necessarily false.
Right, it doesn't make the clause false, but we can simplify it. Right, we could remove this from it. And to turn this clause would just become not x09 or not x05. The point being that when you make an assumption about a variable, you can eliminate some clauses and simplify others. Okay, so we decide, let's start with x00. We decide x00 is true. We produce a subproblem now. Simplified version problem. What do we do now? You assume x01 is true. Simplify the problem. So suppose you keep making that assumption. 0 is true, 1 is true, 2 is true, 3 is true. What's going to happen eventually? Yeah?
You're going to fail one of the clauses.
Maybe. So either we're going to get stuck, we're going to get to a situation, let me back up. Maybe we'll succeed. Maybe making every variable true causes every clause to disappear. So we found a solution, and we report it. Or we may get stuck. We may end up, your goal is to make every, let's look at this one here. Your goal is to make every clause be true. This one here, this one is everything's negated. You want to make every clause true, but if you assume x21 is true, and x25 is true, and x33 is true, suddenly you're stuck, because there's no way to make this clause true. It has to be false. So what do you do when you get stuck? Yeah?
You backtrack one and keep going.
Yeah. You go back to your last assumption that some variable was true, and you say, okay, that didn't work out, let's assume it's false. And you go forward on that basis. Well, suppose that fails and you back up. What do you do now? You've assumed that x25 is true, you've assumed it's false. Both ways failed to find a solution. So there's nothing more to try with X25. So what do? You go back to X24 and try the false assumption for it. And once you've tried every possible assumption you can make and fail to find a solution, then you can report there is no solution. Maybe somewhere along the way you'll hit the right combination that leads you to a success. Or maybe not. Either way, you've solved the problem. But how many different combinations of truths and how many different ways are there to assign true and false, like 50 variables? 2 to the 50th. That's why this is taking so long. It can take a very long time because there's so many possibilities to sift through, even for 50 variables. Okay, so we're almost at 6 million at this point. So I'll give up on that. And let's look at the program. Okay, a lot of this program is devoted to actually generating the random formula. This one right here, random formula, constructs the random formula. So we'll skip. Let's go here to the SAT solver. So this is the class that actually does the solving. So first of all, I just have this property that keeps track of the number of recursive calls made, just so I can display something while it's running. We keep track of the formula we're trying to solve. We're keeping track of the unbound variables, so the set of all variables that we haven't assigned a true or a false to yet. And bound variables are the ones that currently do have a true false value. So initially, all the variables are unbound, and no variables are bound. Okay? So the constructor just sets up those instance variables. You can see it's told, here's a formula, here are the variables in the formula, and the variables in the formula become the unbound variables, the bound variables are empty, and so on. So here's how we do the solve. We first check to see if the formula is empty. So that means there are no clauses left. So clause disappears from the formula when it has been found to be true. So if there's no clauses left in the formula, we return true, we're done. Now we never reach that point in the example I was showing you. Otherwise, we pick an unbound variable to try. And right now I've got things set up so we're making an arbitrary pick. We just take the first variable out of the set, out of the unbound set. We'll look later at how to make a different way of choosing, sort of an intelligent choice. So this is just plain old backtracking, no intelligence involved. So we just pick an arbitrary variable, we remove it from the unbound list and add it to the bound list. And here's where we do what I was describing. First, we're going to set the variable to true. Okay? So we set it to true, and then we call this method prune true clauses. What it does is it goes to the formula and simplifies them all as much as they can under this new the method prune true clauses can tell that variable is been set to true. So it's going to remove the clauses that have been shown to be true, and it's going to return them in that out variable right there. So we get back the clauses that became true as a result of that assumption. So now we have a simplified problem. Our formula has been simplified because the true clauses have been removed. We call solve. If we get true back, we return true. Otherwise, what are we doing? So we make that call to solve. We don't get true back. What do we have to do next? Yeah.
Just adding the clauses we removed from being true back.
Right. We've got to restore those removed clauses back into the original formula. Because we're about to set, so we restore the formula to what it was before. We set B to false and try the same thing. Prune the true clauses out. Try to solve this simplified problem. If that works, we return true. If it doesn't, we add the true clauses back into the formula, clear the variable V so that it's neither true nor false anymore, restore the unbound variable set, restore the bound variable set, and return false. So it's just making two branches at each level. trying what happens when the variable is true, what happens when the variable is false. If it succeeds either way, it returns true. If it succeeds neither way, it returns false. But before it returns false, make sure to restore everything the way it was when it was called. So that's sort of a general form for backtracking. Now, what determines whether or not backtracking is efficient? I can tell you that I've written lots of programs like this that use backtracking to solve puzzles. So I'll see a puzzle I need to solve and I can't, it happens a lot because I solve a lot of puzzles. I can't solve it manually, so I write a program to solve it. So I'll typically write some backtracking solution that tries all the possibilities, and I'll start it running. It'll run for about 30 seconds, and I'll say, man, this is never going to stop. So at that point, I try to make the thing more efficient and run it again. And I keep hacking at it, making it more and more efficient until finally it finds a solution. And then, so as soon as it's fast enough, I'm happy, and I find the solution. So what's it take to make a backtracking implementation fast enough? Yeah?
Just reduce the number of times it has to backtrack.
Well, okay, so one thing is to reduce the number of times it has to backtrack. And that's what we'll look at next, when we look at the clever way of choosing what variable to look at next. So making the backtracking intelligent, more likely to go down roads that will succeed, or a road that will fail fast. If it's going to fail, you'd like it to fail fast. So you'd like to find out there's no solution before you've had to look at every single variable. If you can find out there's no solution by only looking at 10 of the 50 variables, that's good. Okay? So that's the most important thing. But then there are other things that might make the algorithm twice as fast or 10 times as fast. What would they be? Yeah?
Just making the backtracking, like resetting the state fast.
Right. Making the stuff that's going on here faster. What you've got to do is avoid copying the whole state. So it's tempting when you write it, you've got some state that describes the initial problem. Now you've got to generate a subproblem. You can't afford to make a complete copy of the state and then simplify it. Instead, to make backtracking work fast, you've got to take the existing state and modify it. And then when you're done, you've got to restore it. That's what you see me doing here. So like up here, okay, I've got to change the unbound variable set, and I've got to change the bound variable set. Now, one thing I could do is to copy both sets. And once I've copied them, and pass those sets as parameters. And then after I've copied them, I could remove V from one and add V to the other. But that would be very expensive, copying all those sets, especially if you got 1,000 variables, that's a lot to copy. So instead what I do is I just take, unbound variables is just an instance variable. I remove V and I add V. And then before I return, I do the opposite. I add V back and remove V from. So it just takes constant time to update the state instead of copying, which would take a long time. And the same thing goes with the formula. See, right here, I don't copy the formula and then remove the true clauses from it. What I do is I remove the true clauses from it and save the true clauses, so later I can put them back in. So that's sort of a hallmark of an efficient backtracking algorithm, that the manipulations that are made to the state are typically change the state quickly, ideally in constant time, although per and true clauses is not constant time. But we modify the state as quickly as we can, do our search, and when we're done doing the search, we restore the state to what it was before, to avoid the copy. So that's absolutely key. Okay, so let's. I'm going to run the program again, so I've got something to point at. Now I told you when it chooses what variable to expand next, it's just taking the first one out of the set, so it's arbitrary. Can you think of a better way to choose a variable? Yeah.
You pick the one that's used most in the formula.
Okay, maybe you pick the one that is used most, that appears the most time. So you could do a pre-processing step. You could count how many times each variable occurs in the set, in the formula, use that. That's one idea. What's another idea? I want to point out that whatever idea you come up with needs to be fast. right? You don't want to do something really expensive to decide how to pick the next variable. You gotta be, you gotta be able to do it fast. So yeah,
Could you find one that's always true or always false?
find one what?
Variable.
How could you find it, what do you mean by one that's always true?
It's always either has the hashtag or doesn't. The bank.
Oh, I see. So looking for one that's never complemented or never not complemented. Okay. What's your idea?
What you could do is just try and figure out which variables would automatically make one of these true, automatically make one of them false. So anytime it's disjunctions, you want something that's true, and anytime it's conjunctions, you want something that's false.
Okay. So anything, if we can pick a variable that's guaranteed to make a lot of clauses go away, that's good. So when I told you I write programs to solve puzzles, that's what I find myself doing, as I'm thinking, how can I make a choice intelligently? How can I decide, you've got your choice of all these variables to make true or false. How can I pick one that's going to tend to shorten the depth of the recursion? So this is what I did here. You can't tell from this. Most of the clauses have 3 variables in them. Some of them, in the initial formula, some have only 2 variables in them, and some only have 1. There are not many like that. But after the algorithm is run for a while, there will be clauses, where variables have been eliminated, and there are only 2 variables left, or 1 variable left. And so, let's take the following strategy. If we're going to look at the clauses, if we can find one that only contains 1 variable, we're going to pick that variable. Why is that a good idea? Yeah?
Because it has to be either true or false.
Okay, it has to be either true or false. So let's say there's a clause that just contains X. So if we pick X as true, yeah, the clause will go away, and other clauses may go away, and we'll start do our backtracking. But what if what will happen when we decide X is false? The whole thing ends. So yeah, if it contains X and we decide X is true, we're going to have to do some more searching. Then we come back and try X is false. There's no the whole formula becomes unsolvable because that clause that contains X can't be made true if you assume X is false. So you don't have to do any searching from the false case. So that cuts the tree in half right there. And if you can cut the tree in half at the root, that's a huge win. So I'm going to just change things. I'm going to change the program slightly so that it uses the strategy I just described. If every clause contains 3 variables, it's just going to pick one at random like before. But it's going to prefer picking, if there's a clause with just 1 variable, it's going to use that variable. If there's a clause with 2 variables, it'll use one of those. Otherwise, it'll use just some variable picked at random. So let's change it so that it uses this more clever strategy. And to do that, I just have to come up here and change a constant. Make arbitrary pick versus pick it intelligently. Okay, so I told you these formulas are generated at random, but I'm using a random seed that's the same. So until I change the seed, the problem's always the same. So we're going to be solving the same problem we were before. The only difference is which variables we pick as we're doing the backtracking. What did I do? Okay, that's back to true. What the heck? Oh. We're going to set this to false. Okay? So found there was no solution with 610 recursive calls. And all I changed was how it decides what variable to set the true or false as. And it was just a really, really simple way to make the choice. And remember, the old way, it was 6 million and counting when I finally killed it. So that is, that obviously made a huge difference. because it tends, anything you can do that will change a problem where there are two recursive calls to be made at each level into one where there's only one to be made at each level. If you could do that consistently so that there's never more than one branch at each level, it's not exponential anymore. It's linear in the number of variables. This isn't going to be linear in the number of variables in the worst case, but it worked pretty well. So let's see how well we can get it to work. Up here I can choose a number of variables. So that was 50. So let's see if I can do 100 variables. Okay. So it found no solution. Sometimes there is a solution. So it took 14, almost 15,000 calls to do. If I do it, go to 200. This is far from an industrial strength solver, by the way. Okay, but still it solved 200. Oh, it's still working on that. If I remember correctly, at about 200 it starts to go bad. But actually, that's what the guy gave the talk said too. That the industrial strength solvers can be foiled by just a few hundred variables. Okay, so the lesson here is, hopefully you've seen this backtracking pattern. It's easy to set it, it's easy to do a recursive backtrack. Once you've got one that'll find a solution for small problems and it's not working efficiently enough for large ones, then you've got to turn your attention to making the backtracking intelligent. Find a different order in which to make the arbitrary choices that pays off. And sometimes it's hard to know what'll work. You just try things, and if it doesn't work, you try something else. Now, this is 3-set. What if our goal was to solve 3-set, but we wanted to have an optimization, which is we want to find the solution that sets the fewest variables to true. So we turn it to an optimization problem. Why would the structure of the program have to change quite a bit to solve the optimization problem? So we want to set as few variables as possible to true and still solve the problem. Yeah.
The first solution you come across most likely wouldn't be the most optimal, so you have to
Right.
look for other optimal solutions and make it so your first one is optimal.
Right. So if we want to find the optimal solution, we would find a solution and we would have to say, okay, that's a solution. Let's remember somewhere how many variables set to true. And then we would have to keep searching. So with regular backtracking, as soon as you find a solution, you're done and you stop. But if you're trying to find an optimal solution, you have to keep searching. And if you find a better one, you remember it, and you keep finding better and better ones until you've tried every possibility. So that's a different issue, and we'll look at that next. So let's take a break, and we will look at branching bound. All right, this thing's still cranking along, approaching 3 million, so too bad for it. One thing I want to point out, I had a question at the break. I didn't at all mean to imply that any problem outside of that set NP is not computable. There are plenty of problems outside of NP that are perfectly computable, just not in polynomial time. I was just meant to say that I was just pointing out there are problems that are so hard they can't be solved. Okay, so we looked at 3 set. Now we're going to look at traveling salesman problems. So this is a particular interest because it's this week's caddis problem. What am I doing? Set a startup project. And this here, I'm about to show you, and it's on the it's on the schedule, so you can find this thing. It is a solution to the caddis problem. And in fact, if you take this thing and you plug it in, it'll solve some of the tests. I think it maybe solves 3 of the private tests. So it's a good starting point. In fact, we're going to make it even better. By the time class is over, I'll have a solution that will go up to through 6 of the public tests. And when I discovered that last night, I realized I had to change the assignment slightly. Because I was going to give you full credit for solving 6 public tests. So I changed it to 7. So all you have to do is get one more tick up. Okay? Now, if you want to challenge, see if you can solve all the public tests in the time allotted, but it won't improve your grade. I don't want to make your last week miserable here. Okay, so what this does is it generates a graph of a random size. It generates complete graphs. So that's sort of the worst case for the traveling salesman problem, because in a complete graph, every vertex has an edge to every other vertex, and so there's lots and lots of Hamiltonian cycles, and you're trying to find the smallest one. So that makes things harder. At least I think it does complete ones. It certainly does dense graphs here. So let's think about what it will take to do this. How would you describe this as a backtracking problem? Suppose you were trying to find a Hamiltonian cycle, not necessarily the smallest Hamiltonian cycle, but just one Hamiltonian cycle. It starts somewhere, visits every vertex, and then goes straight back to where it came from. How would you structure that as a backtracking problem? Yeah?
You just make a choice and then go making choices until you reach the point where you have to repeat an edge and then backtrack to. Okay, that's a pretty high level description, but essentially, yeah, you begin with some vertices, right? So you got to pick one to start. You got to pick a start vertex. Now, does it matter? Is some choice better than another? If your graph is, let's say the graph is complete. No. Every vertex is going to have to be involved at some point. And if the graph is complete, really no vertex is different, any more interesting than another. So you pick some to start at, so let's say you take vertex A to start at. Now, you've got a bunch of choices to make, right? You've got to pick which edge to follow out of A. Which edge to follow first. And in a backtracking approach, you just try them all. You try this one and then that one. That fails, you do that one. And each time you make a choice, you've got a recursive call. Now you've got more edges to choose from, and so on, until you close up. Now, let me show you how that shows up in the program here. Let me see here. Here's the solver. So let's look at the parameters. Current vertex. So current vertex is the vertex out of which we're trying to extend our path. So we've created a path from an initial vertex to this current vertex, and we're trying to somehow solve the problem. Current total is the current weight of the path so far. So we've built a path so far that ends at current vertex. No, that's not right. Let's read the documentation here. Okay, yeah. So the cost is current total, and the length is current length. Yeah?
Oh, Professor, I just want to make sure that you are recording.
Okay.
I am pretty sure you're the only one all semester that has done that. And I am. It says, yeah. Thanks for asking. Okay. So current vertex, we've extended it. Yeah.
So in a complete graph like this, is the only time you get stuck, can you only get stuck by basically going back to the starting vertex before you can do the rest?
Yeah. So the Hamiltonian cycle problem is really easy to solve in a complete graph. You can never make a bad choice as long as you don't choose to go back to a vertex you've already visited too soon. But if we turn it into the traveling salesman problem, suddenly it's really hard because we've got to look at every possible Hamiltonian. We'll avoid doing that, but in principle, you got to consider every possible Hamiltonian cycle. Okay, so let's see what it does. If the current length is v minus 1, what does that mean? Suppose that we found a path from the starting vertex and it's of length v minus 1. We've got v minus 1 edges in this path. Okay. Well, it means that there's only one more edge to add because the cycle will have v edges. And you don't even have to calculate what edge do we have to add? From there back to the beginning. So the problem is sort of solved at that point, assuming, as I am, that there's an edge. And so I'll come back to this calculation right here. So if you can, in a complete graph, if you've gotten to a point where there is, all you have to do is add in the edge from where you are to where you started. And I'm assuming you started at vertex 0. There's nothing more to do. You've found a cycle. Now, suppose you're not at that point yet. So what I'm doing is I'm looking at every vertex there is, but I'm ignoring the vertices that are in the visited set. So the visited set contains vertices I've dealt with already. So I don't care. I'm looking at all the vertices in this loop, but I immediately disregard vertex 0, let's say, because vertex 0 was one I started at, so it's in the visited set. Maybe vertex 7 is one I visited in the past, so it's in the visited set, so we ignore it. But if it's not in the visited set, we're going to try experiment with visiting it by adding it to the visited set. Then we make a recursive call where that's our current vertex becomes this new vertex. Our current length goes up by 1. You can't see that, but it's current length plus 1. And our current total goes up by the weight of that edge from the current vertex to the new vertex. So make that recursive call, and then after it returns, we remove visited from the visited vertex. So updating the state is very simple. Okay? So that's the this is even simpler than I didn't show you a lot of the code for the 3-set. There's a lot of code that dealt with representing the clauses and finding the true ones and so on. This code's a lot shorter, and you can pretty much just see the whole method right there. So let's look at it and make sure you understand it before we worry about making it better. And let me indent this so you can see it. So, questions about that? What will happen? What's the first call to this look like? What will the 3 parameters be the first time you call it?
0, 0, 0.
Good. 0, 0, 0. When we first call it, the current vertex will be 0 because I just always start at vertex 0. The current total will be 0 because we haven't added any edges yet. We just have a starting vertex. And the current length is 0. There's no edges. So you'll call 0, 0, 0. Now there's this instance variable visited that keeps track of the vertices that have been visited. Initially it's empty as well. So what will happen the first time it's called? Current vertex is 0. It's not long enough yet, so it's going to do this. So what's going to happen? How many recursive calls will it make? Okay? It will make, I've got to take something back. I said something wrong about the visited set. Initially, it can't be empty.
It's gotta have 0 in it.
Right. It's got to have 0 in it. It's got to have a start vertex in it. So we come here, we look at all v vertices, The only one we're going to ignore is vertex 0. Vertex 0 will already be in the visited set. So we'll ignore the 0. We'll look at the other v minus 1 vertices will be of interest. So we'll like take vertex 1, add it to the visited set, and then we'll try to solve the problem of starting at index 1 with a current length of 1 and a current total, which is going to be the weight of the edge from 0 to 1. Try to find a way to solve the problem. And then when it returns, we'll remove vertex 1 from the set. Try it with vertex 2. Try it with vertex 3. So we're going to try all v minus 1 ways out of vertex 0 to see how we do. If you go one level deep, like after we've added 0 and 2, let's say, then it's going to iterate through all the vertices. It's going to ignore 0 and 2 because they're already used. It'll take all the others in turn, add it to the visited set, solve the reduced problem, and then remove the visited set. So it's just following the same sort of backtracking pattern that we did. Now, if this were, how would this be different? How would this look different if I weren't assuming the graph was complete? So suppose there wasn't an edge between every pair of vertices. Yeah?
You'd have to check to see if the graph value that you're pulling up for the TSP solve isn't null.
Okay. So this part would change. So when we actually all of this in here. It's not enough to know the vertex is unvisited. We also have to check right here that there's an edge from the current vertex to this vertex. So if the graph was not assumed to be complete, this would say, if not visited but contains vertex and there's an edge between current vertex and vertex, then you can do this. But I'm not doing the check that the edge exists because I'm assuming it exists. I'm assuming the graph is complete. Because that's what it says in the CATS problem. Okay. This doesn't solve the caddis problem though, because the caddis problem wants to know not does a path exist, or the code I've shown you so far, that I've talked about so far, just tries all paths out for no good reason. What's up with this up here? So we've chased it, we found a path that starts at 0, visits every vertex, and now we just got to add an edge back to 0, which we know exists because the graph is complete. So what, and there's this global variable called best so far, and best so far starts out at infinity, let's say. So what's that statement doing? Yeah?
Every single time you find a new valid cycle, you're comparing it, the total weight of it to the previous cycle that you found.
Okay. So best so far is the total weight of the lightest Hamiltonian cycle we have found so far. And so every time we find a way to close the loop, because we're at the last vertex, what we do is we calculate the weight of the current cycle we found, which will be the total up to the last vertex, plus the weight of the edge back to 0. So that will be, this is the Hamiltonian path that we found. This closes the loop. And so this sum is the total weight of a Hamiltonian cycle we found. If that total weight is less than best so far, we need to update best so far. Okay? Now, when can we stop updating best so far? When can we say, okay, that's enough. Best so far contains the answer I care about. Yeah.
And you've gone through all the Hamiltonian cycles.
Right. After we found every possible cycle. And so let's go back up to where we call TSP solve. All we do to call TSP solve is we initialize a visited set to contain 0. We call TSP solve with 0, 0, 0, like we said. And then the answer is going to be sitting in best so far. So we write it out. Okay? So that just tries every possible cycle and keeps updating best so far. And then after TSP solve returns, we got our answer in that instance variable. Yeah?
Going to the exact path that
Okay.
produced the best so far, would we have to run it again and just find a cycle that
Well, no. Let's think, what if we had to, for the caddis problem, you're just reporting the actual weight of the path. But what if we had to actually print the path out. What would you need to change about TSP solve to do that? Just sort of calculate the path as you go along. Well, first of all, how would we've got to keep track of the path that we're on right now. So how would we do that? How would we keep track of the current path? Right now, we just keep track of its length and its total weight. Yeah?
You know what your current vertex is, right? So you can store where
Yeah.
you're going from your current vertex.
Okay. So just like we had the set visited, which is the set of all vertices that we visited so far. Imagine a list called path that contain the same vertices as visited, except it's ordered. So initially, our path variable contains 0. Every time we visit a new vertex, we add that vertex to the path. Every time we exit, we remove it from the path. That means that when we bottom out up here, we've got a complete list of all the vertices we visited in the correct order. So then we just need another instance variable, best so far and best path. So when you save the best so, if you decide that you're going to update best so far, you also just take the path and copy it and save an instance variable. So when you're all done, you have both best so far and you have the path that calls best so far. So you can calculate as you go along.
So in practice, I know it's not optimal, but if we just sorted the visited list we have right now, this is the
Right.
first number.
If we made, yeah, so if we made visited be a list instead of a set, you know, this becomes less efficient, this test becomes less efficient. But it just means that every time we realize we found a better best so far, we could just make a copy of the visited list, and that's our path. You just have to save it. Then we're all done. Those two instance variables will contain the solution. Okay? Any other questions? Let's see how we're doing here. So I'm going to copy this. And we'll go to Caddis. Actually, I shouldn't have done that. I gotta be careful what it's on the video anyway. Okay, I'm not logged in. What I was worried about was I can see the names of some names that you can't. And so I didn't want to show this queue here and show you things that were supposed to stay secret. But I'm okay because I'm not logged in. So here's the problem. So let's submit it. Now I have to log in, but that's okay. We're using C#. We'll paste the program in, and we'll run it. I think it's going to run out of time there. So it solved the two public cases rather than the 3 private cases. Okay. Good. How do you make it faster? What we're going to look at is a technique called branch and bound. Right? Can you think of a way that we could decide to bail, stop the recursion, realize that we're doomed, that no matter if we continue from the current spot, we're not going to win. We might as well back up and try something different. Yeah.
So all these edges have to be positive.
Yeah, all the edges are positive. Yeah.
So if we're going to recurse, but our current total plus our graph current vertex is greater than our best so far, there's no point in continuing because the total can only go up.
Okay. So the idea would be is if your current total, if current total is already bigger than best so far, there's no point in continuing. So we could just put that first. If current is only going to get worse, so if we got this situation, let's just return. That makes sense? So we're some level deep, and already the length of the path we're exploring is already longer than the best cycle that's been found. We're not going to find, if we keep continuing along this path, we're not going to find anything better because the edges aren't negative. So we might as well just return right away. That cuts off a bunch of recursion, yeah.
Is this still for a complete graph line?
It will work even if it's not complete.
Okay, so you could maybe find a way to check if there's even a path back to the start.
Okay? So if it weren't complete, in fact, we'll hold that thought because this is complete. This is going to spill over into next time a little bit. We'll think about what to do if the graph isn't complete. But for the caddis problem, it's complete. Let's see how this pays off. I actually don't know because I didn't try this last night. So we'll go here. No, I tried something better last night. So. Here's the program. So before we got like the 2 public cases and the 3 private cases. Well, it looks like that isn't going to pay off. Okay? Can you think of something to try to be a different way we could do the pruning? The idea about branch and bound is just stopping the recursion when you realize you're doomed. Yeah?
Would it be like the same thing that we did with caching with other stuff? You can just say like, if you have a vertex that you're currently at and some set of other vertices to still visit, like you can just cache that result.
Well, there is an algorithm, a dynamic, so sort of the plain brute force traveling salesman problem implementation is n factorial, O of n factorial, because in a complete graph, that's just how many cycles are to consider. There is a dynamic programming algorithm that turns out to be n squared 2 to the n. And if you look on the leaderboard for traveling salesman problem, the top scores are using that algorithm. But I'm after a branch and bound algorithm here, simpler to come by. How could we improve this bound? What do we know besides the fact that the current total is? How can we improve our estimate? What we want is an estimate of how much it'll take to finish. A lower bound on how much it'll take to finish the cycle. Yeah?
Do we have any edges that are like 0 or are they all one?
They're all positive.
Are they all one? Could you like check to see how many vertices you have left?
Okay. So we can, to the current total, we can add the number of edges because each edge is going to cost at least 1, right? And so if there are like 10 remaining edges, we can add 10 to the current total because we know that the 10 edges are going to have a weight of at least 1. So I know current length. So what I want is something minus current length. Yeah. Oh wait, v is a variable there. So it's going to be v minus. Okay. So that gives us a better lower bound estimate on how big the current path is going to be. So that'll tend to cut off more.
Do you want to add or subtract that?
To current total, I want to add the remaining,
Does that make it a bigger number?
the number of remaining edges so that it becomes bigger. Because if we continue our current search, we're going to be at least that big. And if it's bigger than best so far, we might as well just back up and try something else. Okay, so that's a different bound we're putting. Let's see if that helps. That is more there. So we've got one more test case that way. Okay? So we're making some progress. So the game you have to play is figure out better and better ways to estimate, to get a lower bound on the best you can do if you continue where you are right now. Can you think of another way to put a, basically we're saying that every edge yet to be added has to be at least weight 1. Yeah?
Would it make it slightly better if you made it greater than or equal to?
Yeah, that's true. Greater than or equal to would make it slightly better. I don't know if it'd make any difference, but yeah. That's an obvious improvement, yeah.
Should you find the smallest weight possible and
Okay.
multiply that number there?
Right. Suppose the weight of the smallest edge in the whole graph is 50. Rather than adding 1 for every one of those edges, we just multiply that by 50 and we have a better bound. So we can pre-calculate the lightest edge in the whole graph and use it. So let's take lightest. So we'll multiply this by the weight of the lightest edge. We were assuming before that 1 was our lightest edge, but maybe it's not. So then I'm going to come up here and let's just do it this way. And let's see. Tell me if I'm getting this right, because okay. So what I'm doing is, as I'm reading the data out of the caddis box, I'm just reading the edge weights out. And as I read them, I am, lightest edge starts out infinite. And as I read each successive edge weight, I take the min of lightest edge of it. So when this is all done, I should have the lightest edge of the entire graph. Yeah?
I think we need to account for zero weight edges, so like edges to itself, right?
I think all the edges are, even the self edges are non-zero in this.
Okay. Right.
But you're right, I'm never interested in a self edge.
Yeah.
And so I could improve this by ignoring the self edges. That might give me a better bound, but I can't do everything for you. So. Let's see how we're doing there. There we go. Okay, you just got to check that last box green. So the game to play is to think of ways to make that bound better still. So in the 2 minutes we have left, let's brainstorm. What can we do? Yeah. Okay, so you could, each time you visit a vertex, you have more information. You could sort of recalculate from the vertices remaining what the lightest edge is. But what you've got to worry, though, is you've got to weigh that advantage of having that better information against the cost it takes to compute. Yeah?
If you're trying to minimize something, you start by taking the shortest path and hope that was the faster option.
What do you mean the shortest path?
Like if you're trying to find the shortest Hamiltonian cycle, well, searching for a Hamiltonian cycle, you could check the shortest paths that were available first.
Yeah, but I think there are tricks like that would make sense if we're working on a non-complete graph. But this one is complete. I can think of one idea. Yeah, you can think of one.
Could you use some sort of greedy algorithm to find a relatively short path so your minimum is small from the start?
Okay, so I think that's what he was suggesting as well. You could imagine just quick find any path. And make that your lower bound. And then I'm not sure if that would win or not, because since the graph is complete, you're going to quickly find a path anyway, a first path anyway. Okay? Why is assuming that all the edges are going to be at least the weight of the lightest edge? How could you improve on that? Rather than assuming that every remaining edge, yeah.
Could you guess that it's like the average weight?
Well, if you start saying, oh, it's going to be the average weight, you're going to get in situations where you're not running out of time, you're getting the wrong answer. So you got to make sure it's true lower bound. Yeah?
Could you start with the lightest edges instead
Okay.
of just the lightest?
What if you had a list of the V lightest edges? Okay? Think about that. How could you use that? If you could easily calculate the V lightest edges once, then I bet you could use that to improve upon your bound. Yeah. So I'll just end by telling you, when I made up this problem, the way I made it up was I did it in Java. I just sat for a while and thought of all the different ways I could do branch and bound, and it got me to where I could solve the number of cases there are. I didn't do anything heroic. I just tried things till it worked. And what I found in the past is, if you try to get all the way, all the check marks, it basically takes one good idea per check mark. One good idea of how to improve the bound. And you just have to come up with, instead of 4 good ideas, you got to come up with 1. So. Have at it. Yep.